please welcome Felipe García-Ramos for the second part of his mini course on the local theory of entropy.
Okay.
Remind some definition.
Yes. There's. So okay, what I will not define will be again a topological entropy. So this is very classical. I don't think I'll remind again, but I'll do. So the main, I think that the main theorem that will prove the last time is we'll take the open cover generated by these two sets. These are subsets of X. We have that the entropy is positive if and only if K1, K2 positive density independence.
Could you remind this latter definition?
Yes. So on the independent set, if for every finite and function that goes from f to 1, 2, there exists a point x such that Tn of z is in k fi for every I in F. And positive density, we gave a different definition, but you can just think that this set I has upper density in the classical sense.
Belongs to
KFI.
Yeah, and then
For every I in F. So sort of like
precisely for every I.
Yes.
Precisely.
So that means in this set F, you can choose one or two, and you can always find a point that will be in those. So that will fulfill your requirement.
What's interesting is this is condition about K1, K2.
Yes, this is independent set
For left-hand side condition is about complements of K and K.
Yes. Yeah, because this is about covers.
Okay, nevertheless, here is some independence of complements,
Yes.
and here is some independence of sets.
Yes. Yeah, but what we want is that independence on these sets and here entropy on the complements. Yeah.
I see.
Uh-huh. Yeah. There's some play here. So somebody else. So regarding measure theoretic entropy. So with measure theoretic entropy, things can. I mean, you don't have covers anymore. You have partitions, and but you can. There's still some form of this theorem, but what changes is instead of there exists one, you ask that there exists a set with positive measure. So you want many such points. You want these points to have some positive measure, and then you can also characterize positive. So I will not get into that. That is just regarding this question from last time. And then, okay, so here we're using positive density, which right now you can think of like upper density, although we were using something stronger, saying that for every finite set there exists a subset that has some proportion, and we didn't need limits, but it's okay. So something that has been very interesting with this, after the introduction of this result, is that you can play a lot. Instead of positive density, there's many other notions of for subsets of numbers, and so some people have been playing with changing the notions here, and some like there's been connections with other areas. So in particular today. I want to talk about what happens when when independent sets, so I'll be more formal, have bounded cardinality. Okay, this is kind of like the topic I want to talk today. So instead of asking for positive density that is very strong, I will ask like, okay, so instead of okay, so I'll be more precise, but first just let me say some corollary.
If you take instead of just two sets K1, K2, if you have some n number of sets, does it change something?
Okay, I mean it certainly changes the definition. You can still play, and it's something stronger. And yes, I mean in some situations it's interesting to study these more sets. For example, one of the applications of this result is related with the Lie York chaos. And if you want to apply it, you need to take bigger sets.
K1, K2 here, open sets.
They're closed sets, closed disjoint sets.
So just can be K1, K2, just each of them 1 point. Yes. So it looks strange that we have precisely jumping trajectory from one.
Yes, but if you consider 1 point, this this cover will they will cover all the.
And entropy is zero. No, I say because here.
Yes, so entropy will be zero. It will not be positive.
So this is not possible.
Uh-huh.
Trivial and
Yes.
I see.
Yeah, and actually, so okay, these were 2 sets. But actually, a dynamical system has positive as if and only if there exists K1, K2, let's say there exists an open cover Q2, where these are not dense. And the complement has independence set of positive densities. And to get this corollary, what you need is some lemma that tells you that if you have positive entropy, you will have positive entropy on sets of size 2. So this is kind of elementary lemma. So in some sense, but the interesting thing about this corollary is that it's a characterization of positive topological entropy, because this was just like a more local version, because this was only with regards to this particular. But this corollary tells you, okay, if you have positive entropy, you will find these sets that have independence. Okay, so now what happens if you cannot find sets with positive density, but still you can find sets with independence? So this, we will be able to relate this notion to another notion of entropy called sequence entropy. And this, so let me, I'll define it here. So, and sequence, so I'll tell you, okay. So, but before defining sequence entropy, I want to tell you kind of like the most simple dynamical systems. So now, today I want to go like in a different direction. So start with the more ordered systems and start building up, like seeing layers of more complex systems. So the most simple systems are the equicontinuous systems. So what this means is that the family the powers is equicontinuous. Okay, so example, rotation on circle, odometers. So you'll notice that rotations in circles are actually isometries, which is stronger than equicontinuous systems, but isometry is not a dynamical property. Actually, equicontinuity is the dynamical property that contains the isometries. So these are like the most simple systems because basically everything stays. There's not a lot of movement. Obviously, these systems have zero entropy. So these are very simple systems, and I would say they are very well understood. Continuum systems have zero topological entropy. But actually, they have a much stronger let's call it SI sequence. The limb sub. So this is very similar to entropy, but now we are only looking at a certain instead of looking at all the sections, we are only looking at in a subsequence. So maybe we look here and then we don't look what's happening here, and then we look what happens here, and then so we are making jumps. So for equicontinuous systems, this will be 0 for every S and every alpha. So this is much stronger than just zero entropy. So a question is you could ask, okay, imagine that this value here is 0 for every subsequence and every alpha. Is it necessarily equicontinuous? And so the measure category, which I'm not giving definitions, but I can also define entropy with respect to a subsequence. Kushnirenko. Every measure preserving transformation with zero entropy with respect to every sequence is isomorphic to an equicontinuous system.
So the question here is, what is the sequence SI? How do you determine the sequence SI?
Right now it's any.
It's any.
Any. So right now I gave a system and I gave any sequence.
Maybe it's better to use the word every.
Any
is linguistically not clear.
Yeah.
Every.
For every. For
Because if you put instead of for every and some sequence, then I think topologically the converse should be true.
Okay, okay, so in the measured category, the converse is true. But in the topological, it's not true. It's not true. There are, I'll tell you some examples. This is a very old result of Kushnirenko. I like this result because it's, I think this result of Kushnirenko was the first connection between von Neumann's ergodic theory and Kolmogorov's. Because von Neumann, he was very operator theory oriented. And von Neumann studied this isomorphism to equicontinuous systems appears in the work of von Neumann because these isomorphisms can be characterized using operators and discrete spectrum. So this isomorphism to an equicontinuous system is a very spectral property. And sequence entropy is kind of like more in the sense of what Kolmogorov, because I think somehow, entropy was not available to von Neumann, and because, for example, von Neumann didn't know if the Bernoulli shift of 2 symbols and 3 symbols were isomorphic or not. And this very, you can answer this very easy with entropy. But von Neumann, in some of his papers and books, he asked the question explicitly. So with and then kind of like when Kolmogorov introduced entropy for dynamical systems, this was kind of like a new idea where you could prove more things. But apparently they were like, at the beginning there seemed to be like different theories, but this is kind of, this result of Kushnirenko is like it's like a connection between both schools. So this is also called discrete spectrum, isomorphism to an equicontinuous.
So isomorphism in which sense?
Measure. Yeah, this is measure.
What does it imply to have one sequence for which?
So just one. So just one. I don't know. I mean, it may be something very particular, but not.
One sequence is not enough because you can have
one.
the big distances from time to time.
Okay, so actually one sequence.
You lose a
one sequence will make more sense here because this is an equicontinuous system. So if you look into like the enveloping semigroup there.
Mm-hmm.
I think the only minimal idempotent is identity. And since you have uniform convergence, so there will be a sequence Si such that T minus Si will converge to identity.
Yes.
So that turns out to be, so this turns out to be sort of, identity stuff.
Yeah.
And that will make the entropy 0.
Yes, but even for, yeah, so that's for a particular sequence.
For one particular, so if you have one sequence, the converse is also true.
I don't think so.
No, the converse is not true. Like for this sequence, you get 0 sequence entropy.
Yeah. But not for every. But I'm saying that if you use
for
every, if you say there exists one sequence, then the converse will.
But wait, if
no.
the density is positive, don't we get immediately that the entropy is 0?
Yes.
That's immediate. The whole point is about sequences that have.
Yes, that have back gaps.
So it's interesting to understand such system.
I agree that it must say something, but for a particular sequence, I don't know results. Okay.
Well, I'm sure you know if it's uniform positive entropy, there is no such thing.
Yeah, no.
So that's So it already gives some.
Yeah. But yes. Yeah, maybe it's and actually I think this is something that is not clear and could be interesting is if certain sequences are good for distinguishing nil systems.
Right.
So like maybe if S is some sort of IP set or something. So this I don't know, but maybe some particular sequences are.
Like you have a class, and now you have a class of sequences where it's 0, and now you try to use this in order to characterize the system. Very
Mm-hmm. Yeah, so something. Okay, so then. So for topological systems, the converse is not true. Counter examples. Sturmian shift. I don't know the name of this toplets. I call it basic. Basic toplets, I mean the one that you construct like this, and then you put zeros here, and then you put ones here. And
Is the regular?
yeah, it's like the most classical regular. Not all regular will be satisfy this, but it's kind of like the basic regular example Sturmian toplets. So basically, if you take a continuous system and you take a very simple codification, sometimes it will have this property. So for every sequence and every open cover, this will be 0. So then, okay, so the converse is
like almost sure, almost 1-to-1.
Yes.
Okay, so that's the answer.
Yes.
Okay.
So this is the converse that can be proved. Okay, so first definition. pi equals pi. So these are called factor maps. Subjective. We say pi is almost 0.1. If there exists a dense set such that if you take the image and then take the image, so then you take the fiber and then you measure the cardinality of the fiber. This is equal to 1 for every x. Okay, so this is factor map. If we ask for the factor map to be bijective, the factor map is conjugate. It's a conjugacy. So this is kind of some weak conjugacy.
But G delta is so, no?
If it's dense, it has to be G delta. Because the points that satisfy...
This, yes, exactly.
The points that satisfy this is a G delta set, and so if there's dense, there would be a residual.
What base?
What?
It is again dense.
Dense.
Oh,
So it's kind of, you have this kind of one-to-one on many points, but not on all points.
it's like odometer for.
Yes. So it's kind of like, you have this like. So if this factor map is one-to-one, if it's bijective, then these two systems are conjugate. But now you're saying, okay, it's not one-to-one, but kind of it's not bijective, but it's almost bijective. So it's kind of like a weaker. Okay, now this is the theorem. And so the first is 1, 3.
Which Lee is this? Is this Hanfen?
No, it's one. No, it's not Humphrey. One Lee. Shall we?
Is it Jianli?
No, because this is 2002. And it cannot be Yan Li.
Yes.
Maybe another Lee before. Yeah, but it's Lee. I'm pretty sure it's some Lee, but it's not Yan and it's not Humphrey. And it's. Yeah, we were saying it's most common last name in the world.
He also York, but I think that
No.
he was much earlier.
Yeah, it's also not that Lee. But yeah, this is Wen Huang, Song Xiao, Xiandong Ye. Yeah. Okay, so I'm asking minimal. So just this means every orbit is dense. And then there exists. And the key continues. Yes. And almost one-to-one factor map. Okay, so this is kind of the converse. These are called this type of results are called structures.
You don't like to say sequence topological entropy?
Yes, just I didn't define it.
What? But you have an objection?
No, I don't have objection. It's just the way I just. Because yeah, I mean, I didn't define. I will have to take a sequence. So sometimes what people call sequence entropy will be the supremum over all sequences and over all open covers. So I'm just hoping this is clear, but I don't have no objections with.
Isn't that exactly what you're saying?
Yes. I mean, I just hope this is clear. That it's just what I wrote, what's written here, like zero entropy with when you take. Okay, so this is the result, and so I will not give the proof, but there are proofs. So this result, first they prove it, then I think there are several proofs of this.
But wait, you don't say if and only if.
No.
Because it's not true.
No, it's not true.
Exactly.
Yeah, no.
Every but not every almost one-to-one extension is zero sequence.
Yeah, in a way this result is not that strong, and I'll give you later a better result. This result is not that strong because you can have this, for example, there are examples like this with positive topological entropy. Like you can have like Toeplitz shifts with positive entropy. So obviously this is not true. The converse is not true. So there are several proofs of this result. So first I prove it, I think then there's another, Glasner also proved it. And there's another by Kennedy. So there's, and all these proofs, they use PI towers and the big extensions. So they use kind of like what I want to show today, I will not show the complete proof, but there's another path that uses more basic, more elementary techniques, and the result is stronger. And I want to tell you a little bit about this other path. I will not give complete. I will not give complete proof, but yeah. So I want. There's a way to prove this without using PI towers and this kind of more sophisticated. And actually this proof is uses it's just like covers, open sets, symbols. So it's just playing around with. It's mostly playing around with topology and some measure theory, but I think this technique is more elementary and the result will be stronger than this one. Okay, so first I want to note that next is if the diameter of a set is smaller than delta, then the diameter of the image okay, so it's sort of like saying because the other definition was with points. If 2 points are closed, then the orbit will be closed. And this is more like, okay, if I have a set with small diameter and I start iterating the set, the diameter will always stay small. Okay, so this is actually they're equivalent.
Till now you didn't use retrievability, in fact. Probably this can be also defined without metric.
Yes.
Purposes.
Yeah, they can be. I mean, for diameter you need metric, but there's some ways to define equicontinuity without metric.
On the other hand, I wanted to ask whether maybe here using metric would make things easier.
Metric.
That it is metricism. In all this theory, maybe using metric makes something easier.
I think usually all these proofs, most papers use metroizability. Most papers use metroizability. So yeah, actually in this course I'm only using metroizability. And then sometimes there's some papers.
The notions you use.
Some papers. So I think that for non-metroizability, some results are written for non-metroizability. There's not one result. I mean, but they use some uniforms. For example, for uniform. For uniformity, I think it's usually okay. Without uniformity, then I don't know.
The continuous becomes difficult.
Because
you need the nearness concept.
Yes. Yeah, with uniformity, I think all this follows with a bit extra work. And maybe not everything, or not all results in the theory are written for uniform spaces. Just once in a while, there's some results. But I think with uniform is okay, so now So upper density is okay. If you want me to define it or remind, I can. It's just the taking the lim sup of the proportions. Yeah. Yeah.
Do we plan a break?
Yeah.
Do we plan a break in the middle?
We didn't have a break.
Okay, that's fine.
But would you like? We can
No, no, no.
If you want to go to something, we can wait. So let me write this first, and then I'll explain.
Should it be NNS?
Any?
NNS, the diameter is less than epsilon.
Or so you want to see what's the size?
Yeah, exactly. Should it be for every n or should it be?
No. I mean, you're counting
Yeah.
which ends this happens.
Okay.
And what he's saying is that it's a lot of them, but it's not all of them.
Okay.
So so compare with this is every.
Yeah.
And now, so we're saying, okay, if we take a small set, once in a while it will stay small, but sometimes it will be big, but then sometimes it stays small. So this is so first okay, now I'll call it sequence and topological entropy is rank. So this, I will tell you how to prove this, but later. And then, I think this is. then a minimal. So we have this kind of notion in the middle, and then what we get is so we will have a factor. So this will be, this is a system with that is diameter mean equicontinuous. And we will have a factor to an equicontinuous system. So since this is minimal, this is also minimal, and this will make it uniquely ergodic. And there's a measure here. I'll call it nu ek. This is actually a hard measure because you can see this as a group, but it doesn't matter. So I mean, the thing is, this system is uniquely ergodic. There's a measure here. And now with respect to the measure in the there exists an equicontinuous system X with invariant probability measure nu EQ and a factor map P. I'll tell you now the property of the factor map, which now will be stronger. Maybe, I don't know if it's immediate, if it's clear, it's stronger, but phi is a measure in theoretic isomorphism. Okay, so the previous result was more just focused on the topology, but here we're getting something about measures. This part is stronger than almost one-to-one because it may be a dense set, but the dense set where you have one-to-one could have measure zero, and actually many times it happens that it has measure zero. So this is a stronger. This is a stronger property. So this immediately will give us this also give one-to-one condense. And this is because it's minimal. So once it's minimal, if you have one-to-one, it will be also one-to-one in the orbit, and the orbit is dense. So it will give you a one-to-one, almost one-to-one.
But in the dense state, there is no if and only if calculation.
No, actually, this I constructed example.
Which is the main
Yes.
They are mean.
Ah, no, wait. No. This is a characterization. No. It's not. This is not a characterization. This is a characterization. Okay, so actually this I can change for. This I can change for if and only if.
Yeah. But I mean, this new notion, it's not that it captures now exactly the class of.
No. It captures this property, but not. Okay, so let me. So let me.
Is it there like a conjecture? What would be exactly that class?
With like a dynamical property that is no, I don't think like if zero sequence entropy can be characterized with a structural theorem. I don't think there's. So let me show you what's kind of like the. So I have so most basic examples are, well, if you want here you have periodic systems. Those are the easiest systems. Then you have equicontinuous systems. Then you have zero sequence entropy. These are also called node systems. Then you have here. By the way, this property is called regular. We call it regular because this is how when Tomasz Dobnarowicz was studying toplets, he has a subset of toplets called regular, and those are exactly these ones. These are regular. So regular or diamine. And so actually there's the ones of von Neumann, the discrete spectrum is bigger class. Now this is kind of by the way, another consequence is that these systems are uniquely ergodic.
What is this C? Regular C diamine.
Regular is a parenthesis. That is, that is the same property. And then here we have like zero entropy. So this is kind of the. There's other classes that I'm not going to mention, but there's some other classes here, like for people who like Kakutani equivalence. There's a bigger class here. There's also another class here called tame systems. But from the ones I'm discussing, this is every class is strictly contained. There are examples. There are examples. There are examples in each class that are not. Okay, so now I want to give you an idea how to prove this one. This one is more complicated than this one, but this one, like I'm saying, this proof, we didn't use sophisticated, it was mostly playing around with it. we didn't use previous structure theorems or like PI towers. No, we didn't use any of that. It was just working with the, because this already gives you some sort of it's a lot playing with the equicontinuity. Because I mean, like you see here, it's kind of like some equicontinuity gives you a good factor map to another equicontinuous system. So so this I will not give indications of the proof, but I will. This is the part.
From an extension point of view, there is the maximal zero sequence
Yes.
factor.
Yes. 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 Yes, there's no, I don't know of any applications of this factor, but yeah, you can define it. Okay, so to prove this, so first define. Actually, for the proof, we need to play with some notion related to sensitivity of initial conditions. Okay, here actually I'll need lower density. So imagine here you have to picture you as a very small so epsilon is fixed. So epsilon you can think like a big, and you think of it like a small set. So there exists some epsilon such that for every u, doesn't matter how small it is, if you check the orbit, the diameter will be bigger than epsilon with some density. So this will happen it will happen more or less regularly. And this is kind of like it looks like the opposite of this property. And actually it is. It's not one if and only if the other, because this epsilon is uniform. So and actually if the dichotomy only holds for minimal systems. Okay, so this is kind of basic result. So for minimal systems, you either have this or the diameter mean continuity. I mean, and by the way, it's called mean because density are related with averages. Average. Taking average and taking density, there's a relation. Okay, so and then I need this. This lemma is also this is the combinatorial lemma that we will need. For every function that goes what's this finite such that f of n so notice the image is a subsequence, is a subset of the natural, so we can measure lower density here. So the density is bigger than epsilon.
Trouble with understanding this assertion. Maybe the letter should be 1 minus epsilon. If epsilon is very small, then it is easy.
I mean, there exists some epsilon.
I just read the last line. If you have epsilon close to 0, then it happens often.
Yeah, it happens.
So it should be bigger than 1 minus epsilon.
No, that's too much. Asking that this is 1 minus epsilon is too much.
Then it's okay for every set U.
It should be?
I'm just emphasizing that it should be for every set U. The set U can
Yes.
be whatever
For
format.
any
Yes.
set U, but I said that,
So epsilon is fixed.
no, that it is for any set U doesn't matter in epsilon, because after some time maybe you become bigger than the first piece doesn't matter. What I mean is that if epsilon is close to 0, then it is easier to have diameter
Yes.
bigger than epsilon.
Yes.
So it should be not density of these events bigger than just
But-
epsilon, but maybe 1 minus epsilon.
It's easier, but still it's hard. That's the point. Even for epsilon, it's hard.
Okay, so let's consider epsilon close to 1. So it is very hard to have. So saying
It's hard, but the epsilon, but still the U, you can start with U that has diameter size epsilon divided by 1 million.
Okay, but
So then it still has to stretch.
okay, but if it stretches after some time, then the rest.
But for example, this.
Okay, I don't know. That was my.
So for example, think of a rational rotation or a rational rotation or some rotation at the circle.
But let's consider epsilon close to 1.
But there existed epsilon.
There exists an epsilon.
So I don't choose the epsilon.
About epsilon close to 0. Then it starts to make sense.
Obviously, smaller epsilon easier
Yes.
to satisfy.
Yes.
Okay, but if you say.
But for example, think of a rotation in the circle. It will not satisfy this property even for any epsilon.
Okay, I didn't pay attention that there exists epsilon. So
Yes.
It is about small epsilon.
Yes. Yes. Yeah, because the other definitions were for every epsilon. This is their existence.
I didn't pay attention.
Yeah. Okay. So this is the hypothesis that you have a function that gives you sequences that have positive density. Then there exists such that
I don't follow you. So we take some finite set.
okay. Okay, we have a function. This is a combinatorics. There's no dynamics here. So this is going to be a combinatorics lemma. I have a finite set such that I pick for any point in the finite set, it gives me a sequence. And this sequence has positive density. So let me finish writing and then we can discuss. Okay, it's written here. Okay, so I have a function. This function for every point, it gives me a sequence with a positive density. So it gives me some sequence that has some kind of thickness.
Why did you write f epsilon 1?
So I have epsilon is fixed. When I write epsilon what?
For every x in f epsilon.
This is a point. Because this is okay, no, that's okay. For every f that goes from here to here, such that every image here has positive density, so this is for every x. I want to find a position that many of these sequences have. This is what I want. So I will find one position I, such that if I measure how many x's contain I, it is going to have some proportion. It's going to have some proportion of the set f, and the proportion is kind of epsilon over 2 or epsilon. This can be changed, but epsilon over 2 is fine. Okay. So now I want to prove this. Okay, so I suppose I'm going to do it by going on the other direction. Assume it's not dynamically continuous. So then by the proposition is it has to be sensitive. So now I start with a sensitive system, and now I want to prove a positive entropy. I want to construct a sequence. Now. So this is what I want. Okay, so then imagine we build the sequence up to some Sn. So let's say, because this is going to be done by induction. So imagine we have S1, and we have Sn. And now we want to build the next step. So this is open cover. This is finite. Okay, I'm missing alpha. This is some alpha. This is some finite open cover. Okay, so for every element in the cover, I'm going to have this property here. For every element, I'm going to see how many times this set separates, and it's going to have positive density. And then this lemma, this is kind of the situation of the lemma, because for every point we are assigning, and then this lemma is going to give me the next position.
Wait, which point? Now you said the open set. You said let's take an open
set. This F is the set of open sets here. And then the function is giving us the times when the open sets grow. When the open sets separate, and this is and this with this this is going to be. This I is going to give me the this I is going to give me a next sequence here, and then with this is kind of like the computation, and then you need to measure what happens when you put this new I into here and check that this grows.
So this I it's going to be Sn plus 1.
Yes.
Maybe there are many such like.
Yes. But it doesn't matter, because the sequence we're trying to construct, we don't care if it has it can be very sparse sequence.
But we can care, so
Yeah.
it would be maybe
Yeah.
better result.
Yes.
Probably you should say that I can be taken as big as you wish. Because you don't want to
Yes.
Yes. or-
Yes. I think actually there's going to be many eyes. I think infinitely many eyes. But yes.
But what actually happens for this I, you will have for this proportion of your sets, diameter of t power n of this set greater than epsilon. Is this correct?
Yes.
Oh.
Yeah. So these are points where the diameter increases, and then considering this property. You need to do computations here, and then check that this is going to give you that in the next step there's kind of there's going to be a diversity of the that the subcovers cannot be very small.
Can you do this computation?
I guess, yeah, we need alpha. It's going to depend on the alpha. The alpha needs to be smaller than the alpha. I think the alpha is going to be made of sets that are smaller than epsilon. So the original of epsilon or something smaller than epsilon. Let me see if I remember the.
So ith iterate of each of these sets will have diameter greater or equal to greater than epsilon.
Yes.
Right?
Yes.
Not of each, but of proportion.
Yes.
Epsilon over to proportion.
Yes. So I think, I mean, what should happen is that these sets, when this diameter increase, they're going to have to be covered by the, because this is a refinement. So so you will need at least two sets. When the diameter is bigger than epsilon, you will need at least two of these sets to cover. You're going to need two of these sets to cover as this image here. So this is going to give you that for certain proportion you will need you need two sets to cover this new yeah, so I think this is more or less how it goes. So these sets have small diameter. And so when the sets have big diameters, you need more to cover. And if this proportion is large, then so it's going to be like many of them is going to multiply by 2. So it's kind of like, so the exponential stuff is like, say you start with two sets. And then you take a next step, and then you say, okay, okay, or imagine you have many sets. And I tell you, okay, in the next step, how many sets are needed for the smallest subcover? And you say, okay, there's a proportion of all these sets that actually I'm going to need at least two sets in the next step. And if this proportion is fixed, and actually the proportion here depends on epsilon. So it's like epsilon% of the f's are going to are going to be divided into two sets.
I don't get the implication because here it's like the diameter is big. I'm missing something.
When you take is iterate of each of this proportion of the sets UK, it will become diameter greater than epsilon, so it will need to intersect a certain number of these pieces UK.
Yes. Yes.
It means that when you pull back by is iterate, then a certain number of these UKs will be subdivided.
Yes.
So that's the idea.
Yes, that's the idea. Yes. No, I mean, the thing is, you need to, when you start refinement, you are going to need to cover this, you're going to need to cover these sets that are, so let me think if there's some arguments I can give you, and I'll tell you. But more or less, this is the important thing is that this proportion only depends on epsilon. So of the new levels, you will always find some proportion. So let's say here in the next level of this is n. In the next level, only some proportion you need new sets. But then if this proportion is independent of the level, this gives you the exponential growth. Okay. So let me give you this is kind of, I mean, this result is proved with the techniques of last week. Close disjoint success. Okay, let me write this different. That's zero sequence. Topological entropy. You can only if for every K1, K2 close disjoint sets there exists n such that every independence set for K1, K2 has cardinality. Okay, so this is now to make a connection with independence. The sequence entropy, kind of zero sequence entropy means that there is a bound on how many independent sets you can find. And the proof of this result is almost exactly as the proof of the it really doesn't change too much.
I have a question again about this theorem which you are proven. So here, are you allowed to start with any alpha or you have?
No. The alpha is going to depend on the epsilon. I think we want the alpha to be sets with diameter smaller than epsilon.
I see.
Yes. Yeah, I put it here with alpha made of epsilons. Yeah, so it's not any alpha, it has to be sufficiently fine. Okay, so there's also a connection between and then there's also some so like I said, you can play around with the definitions of so here is kind of like and if so I won't be I won't be very specific, but if a TDS does not have IP independent sets, then if a minimum, then the system is an almost one-to-one extension of a mixed system. So this is another variation of this interplay between independence and is that if now, so first I was interested in set with density, then arbitrarily large sets. But then if I don't want independence on sets that are infinite sums, then this is going to tell me that this system kind of looks like some, it's related to to some near system.
What's the level of order?
Infinity. Order infinity.
We already 15 minutes over the announced time of the end.
Yes. Sorry.
We continue.
No. I got confused with the. No. Let's.
Okay, so let's thank Felipe. Are there any more questions?
What will be next lecture?
So next.
We will continue this.
So next lecture, I want to talk about systems where every factor has positive entropy. So it's kind of like Kolmogorov systems. And I want to talk about how this, how descriptive set theory appears. So like an interaction with descriptive set theory.
Will it depend much on what you told already? Because if not much, I can advertise that it will be a little bit independent.
I can make it independent.
Okay, so
so I would call it.
maybe you give a new title.
Yeah, I can give you a new title. I can send you a new title and abstract.
Many people are now on vacation.
That's true, but still there are some people around. More than we are here.
But this was very nice. I could understand most of it without taking the previous.
Yes, exactly.
Most was reminded. Formulations are not very complicated.
Yeah, sorry, I passed the 15 minutes. I had my mind started 15 because I was checking the clock, but.
It's okay.